All right, so this is Giovanni. I'm gonna continue the presentation where Alex left off. So let's go ahead and review what are the claims that we're gonna be analyzing and testing with the results. Okay, so the paper makes a lot of arguments. We picked three that we specify in the project report as well, and those are the following. So claim one, we're gonna name this with C1. Claim one is that the model will still work when the data is lopsided. Basically, clients in the real world don't hold a fair sample, but the average algorithm should cope anyway. So how are we gonna test this? We're gonna use the same model, same settings. We're only gonna change how the data is split. It's split across the 100 clients. So we're gonna see if the model still holds with with this different split. Then for claim two, the claim is about from the paper is that more work on the phone means fewer trips to the server. In other words, each client trains longer before syncing, so the model needs fewer rounds to get good. We're gonna test that by changing the local epochs from E5 and compare it against E1. And then claim three, we are gonna check if asking more phones per round in fact buys you little gain. So we're gonna test that by uh, basically comparing the parameter of C with zero point 0.1 with 1. In this way, we will see if there is actually no gain at all as the paper claims. Okay, so for each of all these claims, we're gonna run exact same setting. We're just gonna change these few parameters, and then in this way, we can for sure prove if those claims are right or not. So for the first result, we found out that in fact the split converges even when the clients see only two digits. So basically we compare the non-ID against the ID, and as you can see in the graph, both converge at the end. So there was only like less than a point in percentage in the accuracy between the two. So we can confirm the claim with this result. Some things to point out though is that there were more rounds to get to that test accuracy target. So there is a cost on speed. That's what maybe the paper didn't mention as much. And there will definitely more volatility per round. So the at the end of the day, the claim is confirmed, but there are these little caveats that we have to point out. Okay. Then for the second claim, result two, we found out that more local work it actually does buy fewer rounds. That was this paper central trade. And remember, we compare that by changing that parameter and comparing 5 to 1. So whenever we use the parameter 5, that means we're using 5 times more the local computation, more local work. But what did we find out? It actually bought the reduction almost reduced times two the amount of rounds that we needed to take. So it in fact does buy fewer rounds if you use more local work. But if we talk about efficiency only, keeping the parameter as E1 still is a little bit more efficient comparing the amount of steps that it takes to reach the target accuracy. But as far as getting fewer rounds, yes, more local work does get you those fewer rounds. So claim two in this way is confirmed as well. Then this third claim, the third claim was talking about sampling more clients and then seeing how that compares. And when we compare sampling more clients, what we found out is that we just have more cost, okay? So we compare the parameter C 0.1 with 1. So basically comparing 10 clients against 100 clients. And what we found out is that we only save one round out of 19, only a 5% reduction in rounds. So basically, by incrementing all this amount of clients, you are spending almost 7 times the data, but you are only really saving 5% in the rounds. So maybe it's not that worth it at the end of the day. That's what the paper was claiming. So adding more clients doesn't necessarily help. It just increases cost with just a little bit of reduction in rounds. Okay. Uh, Now let's talk a little bit about strengths and limitations now that we took a look at the results. So, what are the strengths of the paper that we are able to confirm with what we tested? So, first of all, there is some communication efficiency because there are rounds being saved, right? We saw how we were able to save rounds, so phones talk to the server far less often, and that's the efficiency that the paper can claim correctly. There is radical simplicity, meaning that the whole method is trained locally, then average. So just by adding these few lines of code, we are able to get some gains, as simple as just adding that. Then we have the comparison between robust to non-ID data. We saw how that only has a 1 percentage point of difference, meaning that's very accurate between the two splits. Then we also confirm that there is better privacy posture because the raw data never leaves the device. Only the model is the one that does. So that's better for the clients themselves. Finally, the approach does give you a tunable dial, meaning that you can change and modify those hyperparameters C, E, and B and see how all that rates computation and communication. So basically, you can adjust how much work happens on the phone versus the network. So these are mostly the strengths of the paper that we were able to prove. Now, for weaknesses, where does it fall short? So we have these different ones. First of all, the algorithm, where does it fall short? We don't really have a convergence guarantee. We are only analyzing purely empirical values. So we can say that it works because the clients are sharing the same starting point. But this is all simulation. This is all us purely empirically analyzing. There's not like a factual guarantee. Then we have the client drifting at higher epochs. So that means if the phones train too long alone, they can drift apart and the average stops helping. Unstable under skew, that means that the accuracy jumps a lot between rounds. In our case, it dropped almost 7 points in one round, so that might be a little bit unreliable. Finally, full model updates. So the entire model gets sent both ways every single round. So a lot of data is being passed around. So those are some, a little bit of limitations. In a reproduction, we didn't have like full control of the federated algorithm. Basically, we never ran the paper actual baseline. So we cannot 100% confirm that speed up number they were claiming. We were only using a single seed per config, so we just ran the experiment once. That might be a little bit limited. Short budget, no learning rate decay. So we ran fewer rounds than the paper. So we cannot confirm one to one same to what the values that they were saying. And then we use the dataset, the MNIST, but all on one laptop. So we didn't really simulate the whole thing using real phones, dropout connections. So our test was mostly simulated. Okay. So, as far as our own experimental findings, we confirm that claim one was confirmed, right? We only have 1 point behind the two splits. So that means yes, the two splits are basically converging. Second claim, remember there's much more cost to compute with just a little bit of rounds gain. And then finally, claims three, we were able to strongly confirm that because we said that one round out of 19 on the C1 parameter against the C.01. So there was like a big difference in there. So what surprised us about the whole thing? How erratic the non-ID training is round to round. Basically, a lot of volatility, a lot of percentage point difference. The paper smooth this figure. So those are values that they weren't really showing, but we were able to see this when we tested our model. There are a lot of volatility in the model. Finally, we did add a byte cost metric, so we were able to measure megabytes as well. So in this way, we were able to see, okay, how much data is needed comparing the two splits. So that was something that made it all easier to visualize. As you can see, we were able to prove all the claims. And then finally, for the ones that are interested, if you want to do a live demo, basically you just need to run these commands. I can go ahead and do one on my side really quick. So basically here, I go to the folder path where my source code is at. In my case, is this one right here. So I'm right here at the correct folder. Then I make sure I run the Python library. That's the VMV. That's what I do here. Then I'm gonna go ahead and run that first line of code, the Python self-test. That's to make sure all our parameter counts are verified against the paper. So as you can see, it all passes, it's all verified. Then we're gonna train with one of the JSON files. We're gonna sample and train an average using just that one JSON file as an example. Here, this is just like a simple live demo, so we're not doing the whole thing, but just to prove how we run the project pretty much. So here, the model starts running. We are gonna get the results eventually, the whole process one by one here. But right now, since I'm just doing the live demo, I'm not gonna like let it run the whole thing, but just for you to see, as you can see, one round, we see the train loss, test loss, and accuracy for each round. I'm gonna go ahead and just cancel the command. And then finally, let's say all the rounds were through. Finally, you just need to do Python make plots, and then that will write your results in the and basically make these images where you can analyze all the results. Actually, those images are some of the ones we put earlier. Uh, so as you can see, this is how we got the whole thing to work. Okay, and that's everything for my side of the presentation. Thank you so much.